All right. So good morning, everyone. Can you please raise a hand so I know that you can hear me? Okay, thanks. Okay, so welcome back. We're discussing the Siegel summation formula. So let me remind you what we proved last time. So let's denote SLNR by G and SLNZ by gamma, so that the space of lattices of covolume 1 is identified with the quotient space G mod gamma, and there's a natural measure on G mod gamma. So this is the G invariant measure on this space. And we proved that it exists, and we proved that it's unique, and we proved that it's finite. So we proved this is the important fact that I want to mention. So this was part of what we proved last time. And from now on, we normalize this measure so that it's a probability measure. In other words, we proved the fact that any measure with this invariance property is unique up to scaling. And once it's unique up to scaling and finite, we can rescale it so that it's a probability measure, and there's a unique such measure. And this is called, I call this the Haar-Siegel measure. Maybe I'll say one word about that terminology. The Haar-Siegel measure on this space. So this is not completely standard terminology. There is no obvious standard terminology here. People often say Haar measure on these quotients. The reason I don't like that terminology is that Haar actually didn't have anything to do with this. Haar proved the existence of G invariant measures on groups. On Lie groups, it's an easy matter to prove the existence of invariance, the existence of an invariant measure, and these are Lie groups. So his theorem was not difficult in the case we're discussing. On the other hand, he proved the existence of the measure on the group and not on these quotients. The first person to, as far as I know, to define these measures on these quotients is Siegel in the paper that we're following here exactly. So he proved the existence of an SLNR invariant measure on the space of lattices exactly for applications to geometry of numbers. And then a theory developed explaining in which circumstances you could find invariant measures on these quotients. Okay, so that's why I'm calling this the Haar-Siegel measure, although often it's called the Haar measure or the natural measure or the canonical measure, etc. Okay, so what did we also prove? So for each f function, which is whose absolute value is integrable with respect to the Lebesgue measure on Rn, we define a so-called Siegel transform. And I'm now going to denote it with this extra p on top. So we construct a function on the space of lattices from such a function as follows. The function evaluated on a lattice L is the summation of the values of the original function on Rn evaluated on all the primitive points of the lattice. And the reason for this letter P in this notation is to remind you that we're only summing over the primitive lattice points. And with this definition, we proved, and last time I used this notation here, but I also used the same notation without the P, without the hat. And today it will be important to keep the P to remind us of that this depends on, this is for the primitive lattice points. And we proved last time that there's a positive constant Cn such that for every f, the integral of f of the transform of f on the space of lattices with respect to the Harzigel measure multiplied by Cn is the Lebesgue integral on Rn. So this is the Siegel summation formula, and let me give this formula the name SSF1, Siegel summation formula 1, and the reason for this 1 is that there's another statement that's also called the Siegel summation formula, which we will show today. So let's denote, again, for a function which is in L1 on Rn. Now f hat of L without the P is the summation of the values of f over all non-zero lattice points. So more lattice points than previously. And then we're claiming three things. First of all, this transform, this function, which is now a function on the space of lattices, belongs to L1 with respect to the Harzigel measure. Secondly, we have a summation formula for it. And let's call this summation formula SSF2, Siegel summation formula number 2. So what's the difference between these two Siegel summation formulas? First of all, the constant is gone. There is no normalizing constant. In the previous formula, we had a constant Cn appearing over here, which we have not evaluated yet. And the second difference is that this f hat is summation over all non-zero lattice points. And in the previous formula, this was evaluation over the primitive lattice points, and we got this constant in front. Okay, so that's the difference between the two formulas. As you'll see, this is the formula that's easier to work with. Last week's formula is the formula that's easier to prove. And the third statement here is that we have an evaluation of this constant. This constant Cn is the infinite series 1 over j to the n, j going from 1 to infinity. So this is the famous zeta function, the Riemann zeta function, evaluated at n. It's just definition. So this is the Riemann zeta function. And this is well known to converge. This is a series that converges for all n bigger than 1, in particular for we're discussing dimensions. So these are integers, at least 2. Okay, so this is what we're going to prove today. Now, it's not very difficult given what we've already done, so let's prove it. So let's we're first going to prove statement number 1, and to prove that a function is in L1, it's enough to decompose it into positive and linear parts. And I'm reminding you that if you look at this formula, if you take a non-negative function f, then f hat is also non-negative. If you take a non-positive function f, then f hat is also non-positive. So the decomposition of this into its positive and negative parts is just the transform of the decomposition of f into its positive and negative parts. So by writing, so what I'm sure you all know what I mean by decomposing into positive and negative parts. What I mean is we can always take a function and write it uniquely as a difference of two non-negative functions, where the absolute value is the sum of these two functions. And so the same is true for this. This is a unique decomposition, and so we can decompose f hat into positive and negative parts simply by taking the transform of the decomposition of f. This is because the formula for f hat maps non-negative functions to non-negative functions. So it's enough for me to prove that this function is an L1 under the assumption that f is non-negative and f hat is non-negative. So I'm allowed to assume that f and f hat are. So I didn't finish the sentence. By writing that, we may assume that f is non-negative. And let's define for positive t, define ft of x to be f of tx, multiplication of the argument by t, then the Lebesgue integral of ft by change of variables if y equals t times x, then the Lebesgue measure by the Jacobian rule, you have to multiply by t to the n. So this becomes 1 over t to the n integral of Rn f of y d vol y. Okay, so let's remember that formula. And now every vector v, which is non-zero and lives inside a lattice, can be written uniquely as jv0, where j is a positive integer and v0 in L is primitive. Right? The primitive vectors are those that can't be written as a multiple of a smaller vector, and every vector can be written as an integer multiple of a primitive vector. And so now we can decompose this formula. Where is it? This formula for the transform, in which we sum over all vectors, into a sum of formulas where we're summing over multiples of integer vectors. So let's write j is a function of v, v0 is also a function of v, and now we can decompose. Our definition of the transform is this, and we just go over all the v's, for which the j parameter, the multiple needed to make this primitive, is fixed. So this is a sum. Like that. And so this is by definition of fj. I'm sorry, missing a sum here. Okay, let me just skip this line because it's obvious. This is fj hat p evaluated at L0. Okay, if I look at this sum inside, then if I define a new function, instead of f of x, I define fj of x to be f of this quantity, then this is the function fj, and I'm summing over all primitive lattice points. So this is exactly the primitive lattice point transform of fj. So I've decomposed the new transform into a sum, an infinite sum of the previous transforms. And now I can apply the formula that I already know for this transform. And I can use the monotone convergence theorem, because this is a sum of, these are positive sums. These are increasing, this is an increasing series. And so I get so I've written f hat as this sum, and so this quantity is this sum, and I'll pull the sum out by the monotone convergence theorem, and so I get the sum over j's. Something's wrong with my stylus, I'm sorry. Okay. To each one of these functions, I can apply the Siegel summation formula that we've already proved, Siegel summation formula number 1. And so each one of these sums is 1 over the constant Cn that we had before, times the sum j goes from 1 to infinity of the integral over Rn of this function fj. And by the computation that we already made for these integrals, this is 1 over Cn. This is summation j goes from 1 to infinity, 1 over j to the n, divided by Cn times the integral of f. Okay, and this number here, let's call it Cn prime. So Cn prime is, oops, for some reason my stylus is not writing properly today. Cn prime is this quotient that you're seeing. It's zeta n divided by Cn. So this is some positive finite number. And so what have we established? We've established that the integral of f hat is finite, because it's this number here. It's a finite number times the integral of f. So this is this proves statement 1. And in fact, it almost proves statements 2 and 3. In order to prove statements 2 and 3, we just have to check that this Cn prime is equal to 1. In other words, that Cn is equal to zeta n, which is statement 3. So this proves one, and it also shows that 2 and 3 follow from Cn prime being equal to 1. So let's prove that Cn prime is equal to 1. So
Can I stop you for a second for a
sure.
question?
Yeah.
I'm sorry, I don't remember when we talked about primitive primitive vectors.
Hmm.
In terms only of definition, we don't directly know that each point in a lattice is a scalar product of a primitive. It's supposed to be a sum of,
Right.
right?
So the definition of, let me change color here. The definition of, or it's not a definition of primitive, it's what we proved about primitive. Let me erase definition. So primitive means that if you take the span over R of the vector and intersect with L, you get the span over Z of the vector. Okay? I mean, primitive means you can complete it to a basis of the lattice, and in we had a characterization of that in these terms, and so if we draw a picture here, this is 0. If you're non-primitive, so this is, say this is V, and this is the right-hand side. The line is the span of V, and you're intersecting it with L, so you're getting these points here, this discrete collection of points. To say that it's primitive is to say that you're generating this line, so this would be the vector V0 right here. So for every V you can find this V0, it's the unique shortest vector in the same direction on that line. Is that okay now?
Yes.
Okay. So I'm trying to show that Cn prime is equal to 1. So let's use we have this formula here, right here. This integral is equal to this integral. And we're going to apply this for a sequence of functions, which are normalized indicators of cubes. So for each capital R, an integer, let BR be the cube symmetric around 0 of side length R. So this is the ball of radius R around 0 in the L infinity norm, if you prefer. And let's let, so the we're going to define a function fr fr of x. Let's just write fr. It's the indicator function of b divided by a constant. The constant is the volume of b to the r. So this is 2 to the r, sorry, r to the n, 2r to the n times the indicator of b. So that's a function of on Rn, and we're going to look at its transform, apply the previous formula to it, this formula here, right here. We're going to apply to this choice of a function. And so let's first understand how this function behaves on a given lattice L as R tends to infinity. So f R of L is the transform of the indicator divided by the volume. What is the transform of a set evaluated on a lattice? This is the number of non-zero lattice points in this set. So this is exactly the number of lattice points in the set minus 1. The minus 1 comes from the fact that 0 is not counted in the transform. So on the left-hand side, we're not counting 0, and on the right-hand side, we're counting 0. This is a ball around the origin, so it always contains 0. And this is divided by the volume. Now, what happens to this quantity as r tends to infinity? There was an exercise on your exercise sheet. It's not a very difficult exercise using a scaling argument that then basically this is one of the characterizations of the co-volume of a lattice. The number of lattice points in a larger and larger ball divided by the volume of the ball tends to the co-volume of the lattice, which is 1. So this thing tends, as r tends to infinity, to 1. And so what? So now I'm going to, I'd like to take this identity here and use the identity for these functions f hat and let do this. This is an identity, so use this identity for each r, and then let r go to 1. Let r go to infinity, so the integrand will go to 1. In order to do that, I need to satisfy the condition of the dominated convergence theorem. So let me write down a claim. There's a function g integrable with respect to the Harzigel measure. So for all r and all L. So this is a function that dominates, it's an integrable function that dominates all of these functions fr. Let's assume this claim, then we can use the dominated convergence theorem. And what we get is the following. So 1, which is the integral of the function 1 on the space of lattices. This is because we've normalized our measure to be equal to 1. This is equal to the lim as r tends to infinity of fr. Okay, in the previous computation, I checked that pointwise fr pointwise tends to 1 as r tends to infinity, and now I'm allowed to switch the order. So 1 is the limit of these frs, and I'm allowed to switch the order of integration and taking limits by the dominated convergence theorem. And so writing down the integral of fr hat using the formula that I already have, the formula that I already have pulls out the constant Cn prime, which doesn't depend on r. And I get this. So Cn prime is equal to 1. Okay? So this argument is actually very, very general, assuming that I can apply the dominated convergence theorem. Somehow the let me just scroll back up for a second. Remember, we're proving this statement, and this statement has no constant anywhere in the formula. There's a normalization of the right-hand side to be a probability measure. This measure here is a probability measure. And then we get this very nice and clean formula. And I'm just saying that this is, we had a previous formula where there was this formula where we did have a constant, and the constant was an interesting constant. It'll be the zeta function, as we'll see soon. But it's kind of a messy formula. And here, It's a very clean formula. There is no constant. And the reason for that is just that's sort of the natural thing to do by all of our normalizations for the covolume and the fact that it's a probability measure. So this is a very general argument. It doesn't really matter much that this is this particular measure. So now we have to prove the claim. So to prove the claim, we're going to show that if we take alpha to be the number 2 to the n, then we have the following formula. Star, the number of points in a lattice intersected with a ball of radius r in the soup norm is less than alpha, which is 2 to the n, times the number of points of the same lattice in a ball of radius 1 times the volume of b to the r. Okay, let's assume this claim for a second and see why let's assume star, this formula, this inequality star for a moment. And I should have said this is a bound that holds for every lattice. Let's assume this inequality star for a second and complete the proof of the claim. So so as I said before, the transform of FR is the number of lattice points in BR minus 1. Minus 1 comes from the 0 point divided by the volume of BR. So this is obviously less. I'll just add the 1 back. And now I'll use star to bound the numerator. And now the volume of BR in the numerator and the denominator cancels. And I want to write the number of lattice points in B1 as alpha times the number of non-zero lattice points in B1, which is, again, the transform of the indicator of B1 plus 1. And so I've bounded this function by this function. This function does not depend on R. And I'll just need to explain to you why this function is in L1. And note that this guy is in L1 by part 1 of the theorem. That's what part 1 of the theorem said. And the function, constant functions, are in L1 because it's a probability measure. It's a finite measure. So this is my function g. Okay, and now I just need to prove this inequality star here. So let's prove the star. Suppose I had k points in the ball of radius 1. So again, let me show you what star says. Maybe I'm going a little fast. This is what star says. I'm trying to bound the number of points in any ball by the number of points in the ball B1 times the volume of the ball times a constant. The constant is 2 to the n. And the point is that this bound should be independent of L. So let me fix L. And once I fixed L, I want to fix this number to be K, the number of points in the ball of radius 1. So the number of lattice points in B1 is K. Then for any point in Rn, let's look at the ball of radius 1/2 plus z. So I'm taking the ball of radius 1/2 and I'm translating it by an arbitrary translation. And I'm claiming that this contains at most k points. Why is that? Let me write that down. So this contains at most k points. Because if you take any x1, x2 up to xl being distinct points in this translated cube, and that implies that x1, xj, sorry, xj minus x1, j goes from 1 to L, is in B1. If you subtract points from a cube of size 1/2, no matter where if you take their differences, no matter where the cube is centered, you're getting, this is true for any norm, you're getting points of norm at most 1. So they lie in the cube B1. And these are distinct points. And so L is at most K. So I've shown you that any translate of the ball B1/2 contains at most K points. And now you just do a covering argument. Now cover BR. BR was minus R to the n. So this can be covered by 4 to the n translates of B1/2, right? In every, did I get this right? Yeah, this has length. Something's confusing. This has length 2r. This has length 1. So why did I write 4 to the, and I need 2r to the n. Sorry. Okay. So the number of points is less than 2r to the n. Something's confusing me here. Time. Why am I getting, I'm getting a factor of 2 to the n missing. 2r to the n. So I'm getting the correct answer, but it's certainly a wrong proof. And I'm missing a factor of 2 to the n somehow. Okay, let's back up. So what am I trying to prove? I'm trying to prove this. And that's what I got. I should have written volume of BR. The volume of B to the R is 2R to the N. There's a 2 to the N missing somewhere. Okay, I'm not sure why I got this. I'm missing a factor of 2. Two R. Okay, let's just go on, even though I'm confused. I'm confused here. Again, let's draw a picture, and probably this will sort itself out. So we have the ball B1. So B1 is minus 1, 1 to the N. And it contains K points. And now we know that if we take any translate of B1 half, so I can think of this translate of B1 half as also the translate of just the cube 0, 1 to the N. So the number of points in any such set intersect L is at most K. So now we have a big cube. Its side length is 2R. So the number so the number of points in it intersect L. Well, it can be covered by each one of the cubes here covers it and contains at most K points. And so we get K times the number of these cubes, which is 2R to the N, which is K times the volume of BR. And so I don't need alpha at all. Surely that's not right. What's confusing me here is that I got something which is too good to be true. I got the bound, this inequality, the number of points in BR intersect L is the number of points in B1 times the volume of B1. And that's not what I claimed. I claimed something weaker. I claimed this is less than this times a constant alpha.
It's
Yeah.
It's might be a stupid comment, but you're sure there's no confusion about open cubes and closed cubes? Because this 2 to the N comes into play once you use open 1/2 things, because then you need.
No, I may be
That's not
counting
it.
with I may be counting with multiplicity. It's an upper bound. If I count
Yeah,
points,
no, I don't see
yeah.
the mistake, but you would get a 2 to the N if you would use the open one. So that's...
All right. Well, something slightly better than I imagined, but okay, maybe it's my lucky day. I don't know. We can maybe think about it over the break. Okay, so this is the proof of the Siegel summation formula. Before the break, let me just remind you of how we used the Siegel summation formula last time to get a bound, kind of a classical bound. This is Siegel's argument. So recall, again from last week, we used formula SSF2, Siegel summation formula number 2, to show that there is L, a lattice L, such that it doesn't contain any non-zero points in a ball of radius R effective, REFF is called R effective, where, what is R effective? Where R effective is the number chosen so that the volume of the ball, this is now the Euclidean ball, but it's not really important. It's the volume, it's the radius of the Euclidean ball for which the Euclidean ball of that radius has volume 1. So using the Siegel summation formula, we could find a lattice which didn't have non-zero lattice points in this ball. Or in other words, for this lattice, the shortest non-zero lattice point had length at least this number R effective divided by 2. So how did this argument go? We're going to return to this after the break. So let me just remind you how this goes. So suppose by contradiction that for all L, for all lattices of covolume 1, this doesn't hold. So this ball intersected with the lattice L contains non-zero lattice points. If it contains, the ball is symmetric around the origin. So if the lattice contains one non-zero lattice point, then it contains 2 because it contains plus V and minus V. So since V in L intersect a ball implies minus V is in the same ball, this implies that if you evaluate the transform, in other words, if you count the non-zero lattice points in the ball for the lattice L, you get at least 2 for all L. As soon as you have at least 1, you actually have at least 2. And then we get a contradiction as follows. 1 is the volume of the ball, which is the integral over Rn of the indicator of the ball. Which by the Siegel summation formula is the integrator over the space of lattices of the transform. Sorry, the transform of the indicator. But we just noted that the transform is always at least 2. So this is a bit greater than or equal to 2 times the integral of, the integrand here is at least 2 everywhere. So this is, and this is a probability measure. So we got that 1 is greater than 2, which is a contradiction. So after the break, I'm gonna keep this little argument up. And after the break, I'm just going to note a very, very small improvement that you can make that looks completely trivial. But in fact, it's not that, it's sort of, even though it looks completely trivial, it's somewhat useful. Okay, so let's take 10 minutes and I'll stop the recording. Okay, so we meet in 10 minutes. All right, let me continue. Can you make a little gesture so that I know? Okay, thanks, Manuel. So, yeah, there was no mistake in the previous bound. I was just, so the notes that I will post will be slightly cleaner than what I just wrote down. But there's no mistake. Everything I wrote down was okay. as far as I can tell. And so, okay, let's look at this argument again and note a trivial improvement. Let me write down the trivial improvement. It really is a trivial improvement, but it's useful to think about it. So trivial improvement is the following. If we have a ball, a Euclidean ball or any ball around 0, whose volume is less than 2 times zeta of n, then there exists a lattice of covolume 1 that doesn't have any non-zero lattice points in this ball. And why is that? Let me just change color here. And so if we assume by contradiction that such a ball exists, then we can look at the formula that I just, the computation that I just made, and let me indicate a few changes in red. So here I'll just write 2 times zeta of n is larger than this ball. Oops. And this line, so just replace R effective, maybe I'll replace R effective by just R. So this line stays as exactly the same. Here now I can, when I arrive at the Siegel summation formula, I can use the second Siegel summation formula, which is just a little bit better because it sticks in constant zeta of n here. And then I get the indicator, so I get exactly the same thing. And I get a contradiction. 2 zeta of n is bigger than 2 zeta of n. So now zeta of n, when n gets large, zeta of n tends to 1. So this entire computation, all that it's doing is increasing the value of this radius, so the R effective, by just a tiny bit by multiplying it by 2. And it's not a very interesting improvement. But I'm pointing it out because there's this little, what we're using here, we're using 2 things. We're using the second Siegel summation formula instead of the first, which just gives a tiny improvement. And then we're also using the fact that every lattice which contains a non-zero lattice point of some length contains at least 2 of that length, just because it contains v along with minus v. And that seems like a very silly improvement, but that tiny improvement is something that we're going to capitalize on in next. So let me remind you of like a central problem in this field, which is we've discussed many, many times, and I'll discuss it one more time in a slightly different notation. So let's define a number, capital delta of n, to be the sup over the volumes of balls, say Euclidean balls, such that there is a lattice L for which the intersection of the ball with the lattice contains no non-zero lattice points. So it's the largest ball that you can make, the volume of the largest ball that you can make that has no non-zero lattice points inside. And in terms of, so here the ball is defined using the Euclidean metric. And in terms of previous notations that we already used, this delta n is 2 to the n times another quantity which we denoted by small delta of n. Small delta of n is the optimal lattice packing density. It's the volume, it's the largest volume of a ball the largest volume of the largest volume of a Euclidean ball that can be packed using a lattice of covolume 1, or the proportion of space that can be covered by balls, Euclidean balls centered at lattice points for some lattice. So this is the quantity that we've already been interested in and we've already discussed several times, and I'll just remind you of bounds for this quantity. So we just showed that delta of n is at least 1. In fact, we just showed, let me just write it down, even though it's, as I said, it's very mild, but let's write it down. We just showed that delta of n is at least 2 times zeta of n. So it's bounded below by a constant. The best known lower bound is linear in n, c times n, for some c. And this is a result with a long history, and so due to, and I want to say a few words about this history. So Rogers was the first to get such an improvement in 47, then Schmidt in 58. I'll say something about that. Then Ball 92, Krivelevich, Litzin, Valdi, 2004, Venkatesh, 2012 or 13. I don't have it in my notes. I think it's 2013. So the interesting thing about this sequence, and let me also write down upper bound is exponential in n. So delta n is less than some beta to the n, where beta is approximately 1.33. It's not 1, it's some constant. It looks like 1 and a third, 4/3, but it's not 4/3. It's some constant bigger than 1 that starts with 1.33. Okay, so these are the bounds, upper and lower bounds on this quantity, and we've already discussed this before when we were discussing similar bounds for this quantity, small delta to the n. And the interesting thing, one of the interesting things here is that all of these improvements, they all use different arguments. And they all seem to run into a kind of a barrier at going above this linear speed. And in fact, it's been conjectured that this lower bound is not very far from the truth. And so somehow, so let me write that down. So there's a conjecture that Venkatesh recently made. There exist positive constants C and R such that delta n is bounded from above by C times n to the R. So in other words, Venkatesh is conjecturing that the growth of this number is polynomial. The lower bound is linear. He's conjecturing that the upper bound is polynomial, and the best known upper bound at the moment is exponential. So there's a huge gap between what's known and what's not known. And I think the reason for the conjecture here by Venkatesh is simply that, you know, this has been a problem that's been studied for a long time, lots of methods, and they all sort of arrive at the same kind of bound. Okay. Now, Venkatesh is a very well-known mathematician. This isn't one of his best-known works, but it's still an interesting work, and we're going to see that the trick that he uses, at least one of the tricks that he uses, is just essentially like just this little souping up this argument kind of a trick. So it's kind of a very simple-minded trick. And another thing to say here is that some of these techniques work for packing by Euclidean balls or in other words, finding Euclidean balls that don't contain non-zero lattice points. So they use the structure of the Euclidean ball. Some of these techniques work for any convex set. Some of these techniques work for any dilates of any measurable set, but they all run into this barrier of constant times n. And Venkatesh's arguments give the best known constant. So now there's also even a kind of a bit of a computation about the constant. And Venkatesh also gets that along a subsequence, the lower bound becomes slightly faster than linear in n. So let me write that down. Theorem. Venkatesh. Yeah, so it is 2014. I now see it on my notes. And let me add the name of Vance, Stephanie Vance, who was a graduate student. Vance, 2011. So there exists nj going to infinity such that delta nj is bigger than, there exists a constant, and there exists nj going to infinity such that delta nj is bigger than 1/2 nj log nj. Okay, so along a sequence, a subsequence, the lower bound gets improved from being linear to something slightly faster than linear, slightly bigger than linear. And that's sort of the best known result to date. And you'll see that the argument is somehow somewhat even silly, I would even say. And Vance was a PhD student at MIT or Harvard, I don't remember when at the time, and she came up with an argument that she thought only improved this constant here for some sequence of nj's. Well, that's what her paper gives you. It gives you somehow, at that moment, it was sort of this bound with the best constant known, but not for all n, but for some sequence of n's. That was her thesis work. And sort of Venkatesh saw this and pushed the idea further, and you'll see how this works. And he got this bound. Okay, let me also remark, this work uses, as I said, the Euclidean structure in a important way. Let me give a prop. So we're going to be sketching the proof of this. First of all, proposition. When we define this quantity capital delta n, we could define the ball that appears there using any norm which comes from an inner product. Okay, so let me scroll back up. Where's the definition of delta n? Sorry. So you could think about this for any convex set, if you like. And then if you do that, for example, for the cube, you could make this equal to 2 to the n, right? Because the lattice z to the n misses the cube, the open cube of volume 2 to the n. So for example, for the L infinity norm, this quantity becomes very large. It becomes 2 to the n. But that's because cubes sort of are a precise and give you an exact packing of space. But we're discussing other bodies, and for the Euclidean ball, you don't have such efficient packings, and that's what this quantity is measuring, really. And I'm just claiming that when you take this soup, since this is in existence over all lattices, and lattices are the space of lattices invariant by linear transformations, you can replace this Euclidean ball by another inner product. So let me just recall that. That's an easy argument that we've already discussed. Let me just recall that. So suppose my inner product is denoted by pointy brackets. So let x, y be some inner product on Rn. An inner product is given by a symmetric positive definite matrix. So this means xy, I can write it as follows. X transpose AY, where A is a positive definite symmetric matrix. And we already saw, and I checked, and it's in lecture 6 of this course. Whenever you have a positive definite symmetric matrix, you can write it as E transpose E for some invertible linear transformation E. And then, with this notation, if you look at the condition that the ball, and I'm just going to write the pointy brackets underneath the ball just mean it's the ball with respect to the norm coming from this particular inner product. So this ball contains no zero for a given lattice. So for a given L, the ball defined by this inner product contains no non-zero vectors if and only if for every non-zero vector, its inner product with itself is at least R squared. And this means that for every Y in, and this X, as we just said, is yeah. Sorry, I'll be fancy here and move this a little bit. I'm not succeeding. Okay, here we go. This X is simply X transpose E X, which is EX, where the round brackets is giving us the standard inner product. Okay, so if we make a change of variables, y equals EX, what this is saying is that for every Y in E inverse L, a non-zero lattice point in E inverse L, the ball, so the standard inner product of Y with itself is at least L squared, which is the same as saying that E inverse of L has only trivial vectors in the ball of radius R. So then the existence of a non-zero lattice point of a certain size in a ball for some norm given by an inner product gives you immediately the existence of another vector in a ball for another lattice for the second inner product. And since the quantity delta is just about existence of balls, where did this go? Once again, the definition here is just about the existence of some lattice for which this holds. Then the soups are the same. Notice that we didn't say that when you make this change of variables, we didn't say that the matrix that we're changing things by has determinant 1, so it may move us out of the lattices of covolume 1, but we can always rescale. This quantity is invariant under rescaling the lattice. Okay, because we're measuring the volume. Okay, so that's the proof of this proposition. So there's nothing special about the Euclidean norm. And what's the main idea of the proof? Sorry, one more thing to say about the Venkatesh theorem here. Venkatesh also proves, as I said, this is the theorem that we're going to be discussing about this infinite sequence. But as I said, Venkatesh also proves, sorry for scrolling poorly. Yeah, Venkatesh in this paper also proves this kind of a bound for all n. And the argument for all n is more complicated than the argument that we're going to show. And okay, but it again uses these nice symmetries of the Euclidean ball, or of balls given by inner products. Okay, what's the main idea for this proof? The main idea is, scrolling back up to this silly computation, the main idea is that here, I want to upgrade this 2 to a bigger number. And if I make this 2 a little bit bigger, then the argument, in particular, if I make this 2n equal to n, then this argument is just going to give what we want. Now, where did this 2 come from? The 2 came from the fact that when a lattice contains a vector of some norm, then it also contains minus the same vector, which has the same norm. And so the number of lattice points in the ball, as soon as it's bigger than 1, it immediately jumps to 2. So I'd like lattices which have the property that as soon as they have a non-zero point inside the ball, they immediately have at least n non-zero points inside this ball. And that's something that we can do. So the main idea is, instead of analyzing random lattices with respect to the measure, the Haar-Siegel measure on the space of lattices, we're going to use a smaller group. H is a subgroup of SLNI, and get a space of lattices strictly contained in the space of lattices, which is an H orbit is equipped with an H invariant probability measure. And such that lattices in the space contain n shortest vectors, at least n shortest vectors of equal length. So they have an extra symmetry. So this H might seem a little bit mysterious to you at the moment. So, I mean, how can we choose certain subgroups of SLNR to get new spaces of lattices which are in H orbit? This may sound very abstract, so I'll just remind you that we already had this for a different purpose in last week's lecture. So Maybe I'll change color because we don't need, this is just a reminder that we don't strictly need for what I'm going to do, but just to give you the idea, to remind you that we've already seen this idea. Last week, we used the group, which was called U at that time, and it was defined as follows. So these are matrices that are n by n, but they have the first column being the first standard basis vector. So XA, X is in Rn minus 1, A is in SLN minus 1 R. This means U is the, I'm sorry. This is the stabilizer inside SLNR of E1. It's those matrices in SLNR that map the first basis E1 of the standard basis to itself under linear transformations. So this is a group, and we saw that UZ, the integer lattice points in U, is the lattice in U, which means there's a U invariant measure, which we denoted by M U mod UZ on the quotient, U mod UZ, and is finite, which is finite. And we also saw that U mod UZ is basically just lattices in the space of lattices of covolume 1 containing the first vector of the standard lattice E1 as a primitive vector. And so this lives inside space of lattices of covolume 1. Now, we didn't really, so somehow in the previous lecture, this was all an auxiliary statement that we carried along with us in some kind of induction, and we didn't really care about this particular statement for its own sake. But what is this showing us? What's the lesson that we can learn? It's showing us that the space Xn contains certain special subspaces in this with some geometric description. In this case, the subspace gives preference to a specific vector E1, and this we can think of this subset space as a orbit of UZ. And why don't I add one more line here? So this is U mod UZ was being identified with the U orbit of the standard lattice Zn. Okay, the standard lattice Zn obviously contains E1 as a primitive vector, so it belongs to this collection, and U is acting transitively on all the lattices, which contains E1 as a primitive vector with this stabilizer. So that's why we get this fact. We get inside the space Xn, which is a quotient of Lie groups, we get other quotients of Lie groups, of smaller Lie groups, and they have special geometric properties. And not only do these subspaces exist, but these subspaces carry measures, nice finite measures, which are U invariant. Now, all the proofs that we were given of giving of these Siegel summation formulas, etc., they didn't really use any special properties of SL and R in any essential way. They just used some equivariance properties for certain maps. There was a diagram, there were certain arrows, and lots of nice things just followed. And so once you have groups acting on spaces transitively with finite measures on them, you can sort of use the same techniques to get similar statements. And that's exactly what Venkatesh did, and he did it for another group. So now I'm switching back to the darker color because now we're going to work with the group that we will need. We're going to go back to this to finding an H that satisfies this property. Okay. All right. So let me write down a proposition. Yeah, I'm sorry. Let me make a slight digression into. Yeah, let me make a slight digression into some number fields, a little bit of algebra, or a little bit of elementary number theory. So let's let zeta n. So you shouldn't confuse this with the Riemann zeta function. This is another notation which is common. It's the nth root of unity. So this is e to the 2 pi I over n. This is this complex number, primitive nth root of unity, i.e. this number to the power n is equal to 1, and to the power j is not equal to 1 for smaller powers j smaller than n. Let's let k be the number field generated by this nth root of unity over the rational. So this is called the cyclotomic field corresponding to zeta n. Cyclotomic field extension. And the lemma from number theory is about the degree of this field extension. So the degree is the so-called Euler-Tauschent function phi of n, which is defined as follows. It's the number of residues mod n that are invertible, multiplicatively invertibles. In other words, it's the number of numbers k between 1 and n that are coprime to n. This is called the Euler-Tauschent function. And so the lemma says that that's the degree of this field. And so I'm not going to prove this precisely, but I'm going to sort of explain to you if you've forgotten your algebraic number fields, basically, or if you never knew. But in any course in mathematics, when you say that, a reminder, that's sort of a flag that for 80% of the listeners, it might be the first time they're hearing it. So I'm going to give you a reminder from, in that sense, of something from algebraic number theory, which is sort of explaining why this degree is this Euler-Tauschent function. And we're going to get a consequence. In particular, there exists a positive constant c and infinitely many n for which the degree of k over q is less than cn, c times n divided by log n. And I should say something about the notation. So the field, this field extension depends on n, but it'll just be too much, too cumbersome to carry the n around with us all the time. So there are going to be lots of statements about this field k, and you should remember that it depends on n. So note k depends on n. All right, so let's give a sketch of proof of this fact. This is not a proof. There's some not completely trivial things inside this, but let's just say something about the trivial stuff. So let's let f be a polynomial with integer coefficients, which is the minimal polynomial. Of zeta n. So zeta n is certainly an algebraic integer because it solves the formula x to the n minus 1 equals 0. Now this polynomial, well, it has another, it's not irreducible because it's got the root 1. So it's divisible by x minus 1. So that's kind of a trivial factorization. So x to the n sort of factorizes like that. And we're looking for the minimal polynomial of zeta n. So the minimal polynomial of zeta n is going to divide this thing. And if n is a prime, then you can, there's something called the Eisenstein criterion, which implies that this thing is already irreducible. But when n is not a prime, this has multiple other roots. Let me just explain why. So if j is some integer, and you look at zeta n to the power j and raise that to the power n, that's the same as zeta n to the power n raised to the power j. So zeta n to the j is also a root of x to the n minus 1. So all the powers of zeta n are roots of this polynomial. And the same argument will give you something extra if GCD of n and j, let's call that d, is bigger than 1, then we can look at x to the n minus 1, and we can just do this composition, but instead of using x, we can just use x to the d here. So we'll write x to the d minus 1, and here we'll have x to the n minus d plus x to the n minus 2d plus dot 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 plus x to the d plus 1. So these numbers, when the GCD is not 1, they're roots of another polynomial that factors this polynomial, and zeta n is not a root of this polynomial. So then zeta n would become a root of some smaller polynomial when you have factors. Okay? And so the we can write x to the n what I'm just saying is that we can write x to the n minus 1 as this is the breakup of x to the n minus 1 into its factors over c, and then we have to think about how this decomposes over q, and the fact is that one can this is the part that's not trivial. So this was done by Gauss and Kummer, I know, or maybe Dirichlet in the 19th century. One can show that the following polynomial, which divides this product, j goes from 0 to n minus 1, x minus zeta n to the g, GCD nj equals 1, this thing has integer coefficients and is irreducible. Okay, so that's the non-trivial part, and so this is called the cyclotomic, the nth cyclotomic polynomial. So this is the minimal polynomial of zeta n. This has to be, this is therefore the minimal polynomial of zeta n, and it clearly has degree phi of n. So that shows that the degree of k over q is the Euler theta function. So that's the first part of this lemma. And the second part of the lemma is this getting this bound along a sequence. So that's just a question about the Euler totient function. And here's the sequence. So suppose P1 less than P2 less than P3, etc., are the primes given in ascending order. And if we compute the Euler totient function of the product of the first k primes, there's a well-known formula. The Euler totient function is a multiplicative function, and so you get P1 minus 1 up to Pk minus 1. And this is the same as, so let's write this as being n. So if I multiply and divide through by n, this becomes n times 1 minus 1 over P1, etc., 1 minus 1 over Pk. Right, I'm multiplying this expression by P1 through Pk, and then I'm dividing the first guy by P1, the second guy by P2, etc., up to Pk. And there's something called the Mertens theorem. So this is asymptotic to C times n over log n. So this is a theorem called Mertens theorem, which is a 19th century theorem. So this is a kind of a result about, which is in the, so it was proved before the prime number theorem, but it's in the circle of problems around the prime number theorem. You have to understand the growth of this sequence to understand the behavior of this product. So that's the lemma. That's what we need from elementary number theory. I mean, I didn't prove the lemma, but I sort of indicated how this works. And now let's sort of use the lemma to outline our strategy. So let m of n be 2 times phi of n. This is now for any n, but we're going to be interested in these n's in a moment, in these n's soon enough. So the n's that satisfy this asymptotic. But now what I'm writing down now is going to be true for any n. So mn is 2 times the Euler totient function of n. And the proposition says that there's a certain lattice in mn dimensional space and a certain group H, which is a subgroup of SLMNR, such that the following properties hold. So the orbit of this lattice is a closed orbit, and therefore it's identified with the quotient of H mod the stabilizer of this point L0. And so the measure M H mod gamma, this is a measure, this is the H invariant measure on this quotient, which we can normalize to be a probability measure. So this measure induces an H invariant measure supported on the orbit of L0 under H, which is a subset, I'm sorry, of the space of lattices in n dimension. And so I'm going to use the notation measure on H mod gamma to denote the measures on this space and on this orbit. So it's the same notation for two objects which are sort of clearly isomorphic, but somehow abstractly they're different. So that's the first statement. We can find such a group and such a lattice. So far, nothing surprising. Like, for example, you could take H to be the U from the previous example here. But secondly, we're going to have a variant of a Siegel summation formula. So let me call it Siegel summation formula number 3 for all F, which is an L1 function on R to the power mn with respect to Lebesgue measure. The integral of F is the integral of the transform of F with respect to this measure. Okay, so it's the same formula that we had in Siegel summation formula number 2, but it's for a different measure, which is now H invariant. And the Siegel summation formula, the F hat is as in the Siegel summation formula that we had earlier. And the third thing, so again, so far, nothing so surprising. We could just use H equal to SLNR itself, and that would be Siegel summation formula number 2. But now we want some extra property. So each lattice L equals the image of L0 under H. So in other words, every lattice in the support of this measure has a group of order n acting on L by preserving a, I'm sorry, I should have added something here. 3. There exists an inner product, which I'm denoting by pointy brackets, such that for each of these L's, every every such lattice has a group of order n acting on it, preserving this inner product, such that non-zero vectors of length L, non-zero vectors in L have orbits of size n. So the group has order n, and it's acting without stabilizers except for 0. It's acting without stabilizers on r to the power mn. So in particular, it's mapping vectors of length, of any length, to n different vectors of the same length. Okay, so this is the proposition that Venkatesh is using. I'm going to take 5 more minutes maybe before the break. Let's just use this proposition to conclude the statement of the theorem. So where did this go in my notes? I'm sorry. Yeah, here we go. So proof of the Venkatesh theorem, assuming this proposition. After the break, we'll discuss the proof of the proposition. So let's let B be a ball of volume n, or smaller than n, any volume smaller than n, with respect to the inner product, this pointy inner product that I wrote down in statement 3 of the proposition. So I take any ball. This is a ball in r to the dimension mn with respect to this inner product. And again, suppose by contradiction that for all L in this space, L doesn't intersect this ball in any non-zero lattice point. Now, okay, so I'm using, notice, I want to prove a bound on this quantity delta n. I'm using a ball. The ball is with respect to some inner product, which is not the, maybe not the standard inner product, but as I said earlier, this doesn't really matter. So I'm allowed to use any inner product that I want. And the contradiction assumption is that all the balls don't contain points in this, non-zero points in this, yeah. I made double contradictions, so I should put in a no. Okay, I'm assuming that all the lattice points have a point, non-zero point inside. As soon as you have a non-zero lattice point inside, you can apply statement 3. So statement 3 says there's a group acting on this lattice. And so for L in the support, and for any L which is in the support of this measure M, can apply the group action in 3 to find that L intersect B contains at least n different non-zero points. Because the norm is invariant under the action of this group, and so is L. And so is B, because it's defined by this norm. And so I'm getting that if I look at the transform of the integrator of the ball evaluated at this lattice, then I get a number which is bigger than or equal to n. And so I use the same logic that I used before. N is bigger than the volume of B. By the definition of B, this is the integral of the indicator of B by the Siegel summation formula number 3. This is let me just write. This is the Siegel summation formula, but now every point in the support of this measure, this function is at least n. So this is bounded by n times this thing, which is n. So I got my contradiction. So this, what does this contradiction say? This contradiction says that the quantity delta in dimension mn is at least n. Okay, so let's play with that for a little bit. And so this is for all n. And let me just rewrite this using the def. So n is being used somehow for different purposes in the lemma and in the question that we're trying to solve. So let me use the definition of mn, but using k instead of n. So mn was 2 times the Euler totient function evaluated at n. So mk is 2 times the Euler totient function evaluated at k. So we're getting this bound here. And let's choose kj tending to infinity, such that the number nj, which is 2 times the totient function at kj, is less than c times j over log j. This I can do by the lemma. And then delta nj is bigger than j. I just plug this in here, and I get that. And that's moving things over in this formula. That's 1 over c nj log j, which is bigger than 1 over c nj log nj. So that's what I wanted to prove. Okay, so this argument that I just gave is exactly the same argument, this trivial argument that we've been using before, but the only upgrade here was that this left-hand side jumped from 2 to n, and it jumped from 2 to n in a dimension which was actually bigger than n in the sense that dimension which was smaller than n. The size of mn is essentially n divided by log n. And then somehow unraveling what this means, we get this, which is what Venkatesh proved. Okay, so what I need to explain to you after the break is where do you get this group H and where do you get this automorphism? So I'll leave up the, this is sort of the crucial property. Property 3 is I'm trying to construct a group H such that lattices in the orbit of H all have this extra symmetry of size n. And the hint is, of course, that it's sort of related to this cyclotomic field that we discussed before. All right, let's take 10 minutes. Okay, so let me continue. Can someone just indicate that that you hear me? Yeah, okay. תודה, אלון. Okay, so we're discussing this proposition. So let's go over the proposition again. And there's some parts of it that I won't say much about, but let me just say a few words about them, and then we'll get to the part that I do want to discuss. So we're trying to find, for any n, we define mn as follows, and we're trying to find lattice, a space of lattices inside this dimension. And it should have the following properties. So there should be a group, or the group acting transitively on the space, preserving a measure. And that's something that I'm not going to explain. I'm not going to explain how you find. I'm going to tell you what the group is, and I'm going to I'm not going to explain how you prove that the stabilizer of a certain lattice, you can find a certain lattice in this group for which the stabilizer is a lattice in the group. That's part of a kind of a general theory in this topic, and it requires some background. I wouldn't say it's extraordinarily difficult or deep, and you'll just see what the group is. In the second statement, we have this Siegel summation formula. And what's interesting about the Siegel summation formula is that there's no constant in front. So we had two Siegel summation formulas. We had something that I called Siegel summation formula number one, where we used primitive lattice points. And then there was a constant here that one needs to compute. And we also had Siegel summation formula number two. And in Siegel summation formula number two, there was no constant. It disappeared. And it's important for our argument to know the constant, if there is a constant, because that constant enters into the proof. If the constant were big or small, this could have an effect. However, you saw when we proved that this constant is one in Siegel summation formula number two, we gave a very general argument. In fact, there's really no reasonable constant if you're using the same Siegel summation formula that we use, no matter what the measure is. There's just no reasonable constant that you could put here besides one, because for a specific collection of functions, and these are functions which are Siegel transforms, so they should be in L1. I mean, they're bounded by a function which is in L1 by generalities about the Siegel transform. For these functions, the sequence of functions, the integrand here tends to 1, and they have volume 1. So the only reasonable constant to put here is 1. So this shouldn't surprise you that there's no constant here. Okay, so that's all I'm saying about number 1 and number 2. And number 3 is what I want to focus on. I want to construct a certain group H, such that all lattices in the orbit of this group have a certain symmetry. The symmetry permutes the lattice vectors in orbits of length n, and it permutes them in such a way that a certain inner product is preserved, and the inner product does not depend on H. Okay, so I'll explain this in somewhat more detail. Okay, so how does this go? So first, let's define H. So we will take H to be SL2 of a certain ring or algebra. So this might be a little bit scary at first. It's SL2 of K, the number field that we saw before, adjoint R, or extension of scalars to R over Q. So let's explain what these symbols mean. Before I explain the symbols, I'll just say that there's, we took K. K was a cyclotonic field, and K has this obvious operation. You can take an element of K and you can multiply it by the element zeta n, which generates it. And zeta n has order n. So what we're trying to do is find lattices for which this multiplication by zeta n gives a symmetry of the lattices. Okay, so what do these symbols mean? So we can think of K as a vector space over Q of dimension, the degree. That's just. And we can, so it's a vector space with an extra operation, which is multiplication. And with this, so the vector addition is the addition of the field. And since Q is a subfield, it becomes a vector space over Q. And multiplication is an extra operation, which makes this into a field. And if we take a basis, let's call the basis x1 x phi of n of k over q, we can consider the a formal vector space over R spanned by these elements. Purely formally, it's spanned by these elements. And so in other words, it's just R linear combinations of these elements, and we can extend multiplication by linearity. So in other words, if you have scalars A1, AI, and BJ, and you form these two formal sums, then the meaning that you give this is this, where this multiplication is multiplication in R, this multiplication is multiplication in the field, and xi, xj, can be expressed as a linear combination of the xi again. Okay, so this is just a formal way of extending the product from the Q vector space, which is the original field, to this formal R vector space. And this is called, such an extension is called extension of scalars. You may have seen this before. Whenever you have a vector space and over some field, you can make a formal vector space over a bigger field. Often this is used when people discuss complexification of real vector spaces to make them complex vector spaces. And what happened to the product operation on this new vector space? This new vector space is what's known as an associative algebra. I'll write okay, so the reason I'm putting the associative and the with unit in brackets is that in some textbooks, when you say algebra over R, so there's somehow different axioms in literature, in the algebra literature, in different places, and some people always mean an associative algebra when they talk about an algebra, and they always mean algebras with units when they're talking about algebras. But so there's some ambiguity in the standard definitions. But what does this mean? So this is an associative algebra over R with unit that is a vector space over R equipped with a plus operation, which is vector space addition. And a product operation, which satisfy the following axiom. So It's so-called right distributive. It's so-called left distributive. This is for all x, y, and z. And it's the multiplication is associative, and the scalars, multiplication by scalars, pulls out of product. So this is for x, y in the algebra, and AB real numbers, and there's a unit. So x times 1 equals 1 times x equals x for all x. Okay, so all of these axioms. So in other words, this is almost a field. We give up on commutativity of multiplication and of the existence of a multiplicative inverse. Okay. Now I should also say that this is actually, in this particular, this is the definition of an associative algebra. In this particular definition, in fact, we didn't give up the commutativity of the multiplication. The multiplication will still be commutative, but that's sort of irrelevant for our discussion. So here's another way to think about what we're doing when we do this. And this concrete way of thinking about it will be useful for us. So here's a concrete way to think of this object, K, with coefficients extended to R. You can view so fix a basis for K over Q as before, these xi's that we had before. Any element x in K can be identified with the vector, let's call it a bar of x, which is the coefficients with respect to this basis. And so every element of K we can think of as a column of rational numbers, and the multiplication rule, so the map y maps to x times y, which is a map from K to K, becomes a Q-linear transformation. And we can write A of x. This is a matrix of size phi n over Q. We can denote it by A of x. So this is the matrix representing this linear transformation with respect to the basis that we chose. So everything that I'm doing is not canonical. It depends on the choice of a basis, but somehow it's more concrete. So what do I mean by this represents the matrix? If I take this matrix and I multiply the vector that corresponds to y by this matrix, I get a new vector, and that vector is the vector of the product x times y. So that's what I mean by this assignment. And so the map x maps to A of x. This is a map from K to matrices with rational coefficients over Q. It's a ring homomorphism, so it satisfies, it respects summations in products. You can check that. I mean, that just follows from the field axioms. So it satisfies a x1, x2 equals ax1, ax2, a of x1 plus x2 is a of x1 plus a of x2. And in fact, it also sends 1 to the identity matrix and respects inverses. So it's a field embedding, in fact, of the field into a certain subset of n by n matrices. And so we can think of this set of n by n matrices with rational coefficients as a dense subset of real matrices of size phi n. And we can think of K, which is isomorphic to its image under this map, as sitting inside, sitting inside matrices, rational matrices of size phi n, and this is sitting inside real matrices of size phi n. And we can just, this is, you sort of shouldn't use topology when it's not really called for, but it begs its use here. So you can just take the closure of this set and you get a collection of matrices, of real matrices, by just taking the closure of the collection of rational matrices that you want. So we can think of the closure of this embedding of K in M phi n R as this object. Okay, so this object is sitting inside matrices of size phi n, real matrices of size phi n densely. Okay, and so that's the sort of the definition, if you want, the concrete definition of this object. And now I want to explain what I mean by SL2 of this object. So, and also let's remind ourselves that we had a formula Mn, where did it go? Mn was 2 times phi of n. So Mn is twice the dimension of these matrices. And we're trying to talk about SL2 we're trying to find matrices in SLMNR, where Mn is 2 times the size of these matrices. These are matrices of size phi of n now. And the way to do that is just to formally make matrices of matrices. And that's what we're going to do. So, oops. Real matrices of determinant 1. That's what this S stands for, as in SL2R, of the form A, B, C, D, where A, B, C, and D are in this extended algebra, which is, okay, so we just stick these n by n matrices, phi n by phi n matrices on top of each other and get these matrices. Is there a question?
I think you want the formula AD minus BC to be equal to the identity instead of,
No. So
or
this
is
is,
it this?
no, this is the, no, I want the determinant as real matrices to be 1. This is called the reduced norm. So yeah, so Manuel is asking a
Okay,
good
yeah.
question. So if I was to require that AD minus BC was equal to the identity as elements of the algebra, then you can think of this as placing phi n restrictions on the difference AD minus BC, because elements of the algebra is phi n dimensional, and when you say that it's equal to 1 is a particular vector. Okay, anyway, this is what I want to do. Okay, but yeah, it's not completely self-explanatory. That it's not the only thing that you might want to do. Okay, so that's the meaning of H. Okay, and now I want to define this lattice L0. We're trying to construct a certain special orbit of this particular group H, and the orbit will be of a lattice O, which is connected to the field, and it's going to be basically so-called geometric embedding of the ring of integers of this field. So what does that mean? Every number field has a so-called ring of algebraic integers. So the algebraic integers are those algebraic numbers that solve a integer monic polynomial with integer coefficients. So the leading coefficient is 1, and that's a ring. So recall, again, in the same usage of the word recall, I'm assuming you know what you may not know. So recall that a number, let's say Z in C, is called an algebraic integer if there exists a polynomial with integer coefficients such that P of Z is 0. That means that that's the meaning of the word algebraic, and the leading, so P is monic, which means that the leading coefficient is 1. And it's a fact, not completely trivial, that algebraic integers are a ring. So they're closed under sums and additions. That's not something you could just prove by the definition. It requires a little bit of a theory. So this, so algebraic integers form a ring, and to any number field K can look for any number field K, we can look at so-called O of K, which is the ring of integers in K. So it's a subring of the field K, and it's a special subring. In the case at hand, so in other words, if K is what we've been discussing, it's Q adjoint the primitive nth root of unity, the cyclotomic field, O of K is Z linear combinations of the generator Zn. So again, if you look at my definition, it's clear that the number Z of n, zeta of n, the nth root of unity, is the root of a monic polynomial. It's the polynomial x to the n minus 1. So it is an algebraic integer, and I'm telling you that any algebraic integer in this particular field can be obtained by taking Z linear combinations of zeta n and its powers, which is a non-trivial fact, but that's just a fact for concreteness. We're not going to use this. And now let's let L0, I'll use the notation O bar of O k squared. And what I mean by that is A bar x, A bar y, where x and y are in. Okay. So I'm using elements of this ring, and I'm putting them, I'm making vectors of size 2 using elements of this ring. But as elements of Rn, they're vectors of size mn, 2 times phi of n. And let's look at the operation of multiplication by zeta n. So zeta n acts on sorry. Zeta n applied to, I didn't mean that. Yeah. Yeah, I don't need this XY thing. So here's an action of the nth root of unity, zeta n, on R to the mn. I just make a block matrix, putting in the matrix A of Zn, which is a rational matrix, in the two summands, in the two diagonal blocks, and I let that act by usual vector multiplication on R to the power mn. So since A is a field embedding, we get that, so A of zeta n to the n is, this is the identity. So this is a group of order n, this generates a group of order n acting on R to the mn. And that's the group that we're going to use in statement 3. Whenever you have a group of finite order acting on a set, on a vector space, you can find an inner product which is invariant under this action. So let be an inner product on R to the mn invariant under the action of zeta n. There could be many, but here's one possibility. For instance, the pointy inner product of two vectors x, y is the sum of the standard inner product applied to their orbits. So j goes from 0 to n minus 1. We take zeta n j applied to x, zeta n j applied to y, and we take any inner product that we particularly like, and we evaluate it on this on these two vectors, and then we take the sum. So since this is an orbit sum, and since this is the orbits are of size n, this is well defined, and it becomes invariant. If you multiply the zetas, if you multiply x and y by zetas, you're just permuting this sum. So this is an example of an invariant inner product. And here's the proposition that we're going to need for statement 3. Each lattice L in the H orbit of L0 is invariant under the action of zeta n. So it's invariant under this group of order n. And moreover, zeta n acts on non-zero elements of L with trivial stabilizers. Or in other words, for any x, a non-zero vector in L, L is as above, it's an element of this orbit. The vectors x, zeta n x, dot, 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 zeta n minus 1 of x are distinct and have the same length with respect to this pointy inner product. Okay? The fact that they have the same length is just because of what I said here. It's just the inner product is invariant under this action. So they obviously have the same length. The fact that they're distinct is something we're going to see. It's sort of trivial from our definitions. And the fact that we're acting is also sort of somehow simple from our definitions. I'll just, at the end, we'll just zoom up. You'll see that if you recall what I stated before, proposition 1 is this proposition is exactly what we need for statement 3 of the previous proposition. Let me just write that down because I don't think we'll have time later. So remark, this proposition proves item 3 of the preceding one. Okay, proof. Let's note that let's figure out the action of zeta n on vectors which come from the embedding that we had. So zeta n applied to a vector of this shape. We take the embedding a bar of a vector x in phi n dimensional space, rational space, and similarly for y, and we apply zeta n. What we get just by definitions is this matrix acting on this vector where these pieces are of size phi n. And since this is a block matrix, this is a of xi n, a bar of x, a of xi n, a bar of y. And that means this is a of xi n x, a bar of xi n x, a bar, sorry, zeta n x, zeta n y. Okay? So it's basically the operation of multiplication in the field that's giving us this automorphism on these pairs of field elements embedded in this way. And so if L equals L0, i.e. H is trivial, then zeta n applied to L0 is zeta n applied to Okay, this is just the definition of L0. And by this computation that we just did, this is a bar of zeta n x, a bar zeta n y, where xy is an OK. But I already said that zeta n is in the ring OK. It's an algebraic integer. And so this quantity is obviously a subset of the lattice that we had before. And since we can apply the same argument with the inverse of zeta n, which is also which is also in the ring, Zn, the inverse of zeta n is zeta n bar, which is a power of zeta n, so it's also in this ring. We get that this is actually the same as L0. This is because zeta n is in OK, implies zeta n OK is contained in OK, and zeta n inverse is in OK, and this implies that OK is a subset of zeta n. OK, so zeta n OK equals OK. So all of that explains this last equality. So we've proved that zeta n is preserving L0, and now let's take a general L in this orbit. Now, so now for H in H, and L being equal to H times L0, so I'm sorry. Let's write H in this form, A, B, C, D. Where A, B, C, and D are in the restriction of scalars of K, the extension of scalars of K, and we have that A, so we think of these as matrices, sorry, and they commute with multiplication by A of zeta of n. That's because this is a field. So multiplication is commutative in the field, and we've extended this multiplication by linearity, so it just stays commutative. So that means that this element A commutes with H. And therefore, so by the commutation, zeta n is preserving each one of preserving this space L. And finally, I need to show that it's acting with trivial centralizers. So if for some V in L, if we had a power of this J which mapped it to itself, in other words, if we had a non-trivial centralizer, then for V in H inverse, sorry, for H inverse V, which I can think of as XY, an element of L0, we would also have zeta n to the J H inverse V equals H inverse V, i.e. zeta n J X equals X, zeta n J Y equals Y. But now these are elements of the ring of integers X and Y. X and Y are not both 0. I should have written V not equal to 0 here. X and Y are not both 0. So J has to equal N. So we get that, that the stabilizers, so we can divide through by, this is an identity now in a field. Okay, so we're getting that zeta n acts on L minus 0 without non-trivial stabilizers. And that completes the proof of this proposition, and completes the sketch that I'm giving of how Venkatesh proved these results. Okay, so if there are any quick questions you can ask.
So for the little question I asked before, whether you want the determinant to be 1
Yeah.
or the thing, it does not matter for this argument, right? You could also just work with the restriction of scalars.
Let me think.
Should
It
look the
just
same.
no. This argument won't care. This argument won't care about it. But you need an algebraic group that has a lattice inside. You want it to be a Q algebra. So
yeah, but the restriction of scalars will still have this property, right?
this isn't exactly that. We're not doing restriction of scalars. I said restriction of scalars by mistake. We're doing extension of scalars of this this algebra. So this you want this to be a real semi-simple group, right?
I meant the restriction of scalars like Weyl of the algebraic group. You start with SL2 over K, then you do restriction of scalars to Q and look at the R points acting on SL2M. And I can think through it on my own.
Yeah. Okay. I think we're doing. I think this is called the algebraic group is not called the restriction of scalars of SL2. It's called the reduced norm elements in 2x2 matrices over K. So I think these two operations will work for some of the argument, but not for the. You just need the fact that this is a semi-simple group here. Okay. All right. So thank you for listening. So we meet again next week, and we'll do more applications of this kind of Siegel summation machinery next week.
Thanks.
Thank you.
Thank you.
Sure.